Hello, everybody. Welcome back. Today we're going to be looking at Unit 4.6, which is all about introducing you to the concept of titration. So let's get started. All right, so the purpose of doing a titration in the lab is to determine the concentration of something. It's an unknown concentration. And there are two parts to a titration. One part is using something that you do know everything about it. You have a known concentration solution, and that is called the titrant. And in this picture on the right, the piece of glassware at the top, that's called a burette. And that is where the titrant is going to be located. The unknown, the substance you are analyzing, is typically going to be found in the flask on the bottom, and that is called the analyte because it's the thing you are analyzing. And the whole purpose of a titration, and there's different types of titration, is to reach what is called the equivalence point. Okay, sometimes in some textbooks it's called the stoichiometric point, which means that you've added enough titrant up in the burette to react exactly with the analyte. So using stoichiometry, if you converted titrant to moles, from moles of titrant to moles of analyte, they would be in a stoichiometric relationship. Okay, and what you typically see is some kind of color change when that point has been reached. If you're doing an acid-base titration, for example, you are likely going to be using something called an indicator that changes color. Okay, so sometimes you will see in a word problem, it'll say neutralization has been reached, or the indicator changed color, or you might see something referring to the end point has been reached, which just means the point at which the indicator changes color. All of this language means the same thing. We have reached the equivalence point. And if you know the number of moles of titrant that you've delivered out of your burette into the flask, that would be a known quantity. You can use stoichiometry to calculate from moles of titrant to moles of analyte, and you can know how many moles of analyte you have down in the flask. So this is just kind of a very simplified visual of how, the different steps in a titration. Okay, so on the far left, it looks like in this case, we've got the unknown acid is in the flask. In step 2, you can see I've added a few drops of indicator. In step 3, I take a reading on how much, let's say it's a base up in the burette. I take a reading on how much base I begin the reaction with, okay, where it is in the burette, those volume markings. And then step 4, I'm starting to add some base to the acid that's down in the flask. And then in step 5, you can see there's been a color change. The indicator has changed color. That's an indication that we've reached the equivalence point. I look at the final reading on the burette, and the difference between the initial and final reading, that's the amount of base or whatever titrant is up there. That is how much it took to reach neutralization. So those are sort of the steps in a typical titration. So let's look at a simple example, and then we'll slightly move up in complexity. All right, if we're talking about an acid-base titration, all right, very often on the AP exam, you will be asked to write out the net ionic equation for that reaction. So I want us to go back through that process step by step and make sure that you remember how to do that. Okay, the first step is to write out what's called the molecular equation. So in this case, I have hydrofluoric acid reacting with sodium hydroxide. It's a double replacement reaction. Here's one of my products, sodium fluoride. And some people write it as HOH, which you can do that if you wish, or you can just simply write it as water. Okay? If you will recall, the next step is to use your solubility rules to decide what substances are going to ionize and which ones are not. So let's take it piece by piece. HF is an acid. If you look in the rules, one of the rules says that only strong acids ionize. Okay, now I know I said to you guys that you only have to memorize the first two solubility rules, and that isn't one of the first two, but I would highly recommend that you commit those 6 strong acids to memory. And ladies and gentlemen, HF is not one of those 6. It's a weak acid. So it does not dissociate or ionize to an appreciable extent. So I'm going to keep it together. All right, sodium hydroxide. It has a group 1 metal in it. It is definitely soluble. It will definitely ionize. Okay, so will sodium fluoride because, again, it has that sodium metal in it. And water, ladies and gentlemen, don't ever split up water. Leave it as it is. Okay? This was now the point at which we canceled out, do you remember what they were called? The spectator ions. And there's only one. So at the end of the day, this is what I'm left with. HF plus OH minus yields F minus plus water. Okay, so in a titration question, as I said, one of the first, if this is free response, one of the first parts, part A, is usually going to say, write the net ionic equation for this reaction, and I just wanted to go back through that with you one more time. Okay, so there's our reaction. All right, I want you to, this is an introduction to you, we're just starting to talk about titrations. If you were to carry out this acid-base titration and you were monitoring the pH as you add more and more base, you would expect the pH to go up, to become more basic. And it does, but it doesn't go up in a linear fashion. It goes up in sort of this S-shaped curve. And ladies and gentlemen, there is a point on this curve that is the most important place. And it's right there. Okay? Where this S-shaped curve is at its most vertical point. If this were our math class, a math class, you might call that the inflection point. That is the equivalence point. So sometimes you will need to estimate that off of a graph. Okay, so it's important that you know where that equivalence point is. Again, it's at the most vertical point on that S-shaped curve. So let's look at something really simple. All right, and then we'll move up in complexity. It says 40 milliliters of 2 molar HF. Now stop right there. When you are given a volume and a molarity of anything, I want you to think about what you can immediately solve for. That is a combination you're going to see 1,000 times over in this course, a volume and a molarity given together. Okay? So we've been given that information. That much will require how many milliliters of 3 molar NaOH to reach the equivalence point. Okay? So I want you to pause your video and see if you can solve this. All right, let's see how you did. Okay, so the first thing that I did was I took the volume of HF and the molarity of HF, the volume they told me it required to get to equivalence. I changed it from 40 milliliters into 0.04 liters. And I got moles of HF. And then remember, being at equivalence means that you can use stoichiometry to get from your titrant, HF, to the analyte. Now, in the balanced net ionic equation, I didn't have NaOH in the equation. I had OH minus, so that's why I converted to OH minus first, and then went to NaOH because that's what the question asked me for. But there's just one hydroxide within NaOH, so it's just a 1-to-1 ratio. And then I used the molarity of NaOH that was given to find the volume. I don't think you'd have to put it back into milliliters, but I did. So that would be the amount required to reach equivalence. Okay? So that was kind of a simple one, all right? This one is not really that much more difficult. It's just going to require a little bit more work on your part, but I want you to try this one. I'm going to introduce it to you. It says, in a separate experimental procedure, the student titrates 10 milliliters of 2 molar, and that's acetic acid. So again, guys, there's that combination, volume and molarity, right there. With a sodium hydroxide solution of unknown concentration, the student monitors the pH during the titration. The following titration curve was created, and there it is. There's that S-shaped curve. First thing it says to do is to write the balanced net ionic reaction, net ionic equation between those two reactants, and then to calculate the molar concentration, the molarity of NaOH. Okay, you're going to need to look at that graph. All right, that's going to give you some information that you will need to calculate that second part. So see if you can do it, pause the video, see how you do. All right, before I pull up the answer, I want to just call your attention to the fact that on this graph here, you are going to need to get a piece of information from it. And the thing to notice here is that the equivalence point is about right there, and I would estimate that that falls at about 14 milliliters, okay? It's just something to kind of pay attention to. It's not necessarily that the pH is actually going to matter in this particular question, but the volume that it took to get us there, that is going to be important. Okay, so let's look at our answers and let's see how you did. Let me pull that up for you. So the first thing to do, guys, was to write the net ionic equation, and that's what you see in letter C. If you're wondering why I'm starting with letter C, it's because this was a longer free response question, and parts A and B, I just took them off. So C was writing the net ionic equation, and letter D was very similar to that question that we just did a moment ago. I took the given information about the acetic acid, and I used it to find moles of acetic acid. Since we were at the equivalence point, I could then use stoichiometry to get to moles of NaOH. And again, pay attention to this number down here. That volume is the one I found off of the graph. So if you're wondering where that number comes from, it came from the volume of NaOH required to get to the equivalence point. Okay, so that was the amount of base that I needed to add to this acid to reach the equivalence point. And then knowing the moles already from the previous step, I was able to find the final answer of the molarity. So that's in some cases, that's what, an acid-base titration will very often ask you, is about something at the equivalence point. Now, titrations do not have to always be acid-base related. They can also be redox related. And remember, redox just means reduction, oxidation. Elements are changing their oxidation states. They're maybe going from +2 on the reactant side to +3 on the product side. Some element is being oxidized while another element is being reduced. Okay, but it's the same kind of situation in redox titrations. Very often an indicator does not have to be used because you can sometimes use compounds that are themselves colored, okay? So you don't have to use an indicator. We wouldn't necessarily need that visual additive to know when we've reached the equivalence point because this chemical itself has color and changes itself when we reach equivalence. So we've got a balanced equation in front of us. Let's read the problem. And I'll show you how this process is really no different than an acid-base titration. It says, a student was given the task of determining the molarity of an unknown concentration of, and that's called oxalic acid. Okay, and I can see it, it's my third reactant up in that equation above. She analyzed a 22 milliliter sample of the oxalic acid by titrating it with 1 molar potassium permanganate, which has a dark purple color. The balanced chemical equation for the reaction that occurred during the titration is shown above. Okay, fine. Well, let's keep reading. There's actually more to the question. It says a total of 55 milliliters of 1 molar potassium permanganate was required to reach the equivalence point. Now, guys, just stop there and think about what you could solve for right now. You have a volume, you have a molarity. You have a mole, you have a number of moles, okay? We're going to see that combination so many times. So letter A says, calculate the number of moles of permanganate ion that completely react. Okay, fine. And then letter B says calculate, remember what brackets mean, calculate the molarity of the solution. Okay, molarity, of the oxalic acid in the solution. Okay, so I want you to try this one. It's really no different than what we were just doing. Pause the video, see if you can answer it. All right, so 2 parts to this problem. The first part simply says calculate the number of moles of permanganate ion, which I can get by simply looking at the information given directly above it, that 55 milliliters, 1 molar potassium permanganate. And you can see that up here at the top, I have used that information to find moles of potassium permanganate, and then I just converted it into moles of just the permanganate ion. So there's my answer to letter A. Then we were to use that information to eventually find the molarity of that oxalic acid. Part B, guys, is no different than the acid-base titrations we were doing, the only difference being that since we know we're at the equivalence point right here, the coefficients in our acid-base reactions just so happen to be 1 to 1, whereas in this redox reaction, the coefficients were 2 to 5, but it's the same process, okay? 0.055 moles of permanganate must have required 0.1375 moles of oxalic acid, which then we were given the volume of the oxalic acid. I can then use that to find the molarity. It's the same exact process. It doesn't matter that it's a redox reaction or an acid base. It's the same processes again and again. So, just a little introduction to titration and looking at the two different types of titration. We will do some more calculations related to acid-base a little bit later on in the unit, and then we will really look into acid-base later on in the year. There's an entire unit dedicated to that. So I hope you've learned a little something, and I look forward to seeing you next time.